Okay, I hope I'm audible to all students who are attending this lecture of mathematics class 12. We intend to start with a new topic within our lectures on mathematics class 12. This is linear programming. Okay, so all students can recall that in class 11th mathematics, we had done lectures on linear inequalities. If all students can recall, okay. Now, in class 12th mathematics, we'll be plotting these inequalities in a graph and we'll be maximizing or minimizing a function subject to those inequalities. Okay, so first of all, let's write the definition. What is meant by a linear programming problem? So we can write a linear programming problem is the one that is concerned with finding the optimal value, that is concerned with finding the optimal value, which can be either a maximum or minimum. Okay, of a linear function of several variables subject to the condition that the variables are non-negative, subject to the conditions that the variables are non-negative and satisfy a set of linear inequalities. Okay, so let's quickly go through the definition. So first of all, before going through the definition, let's write what is meant by linear. So I can write a note. The term linear implies that all the mathematical relations used in the problem are linear relations. All the mathematical relations used in the problem are linear relations. Okay, while the term programming refers to the method of determining a particular program. Okay, so now let's look at the definition again and just note what is meant by a linear programming problem. A linear programming problem is that problem which is concerned with finding the optimum value. This optimal value can either be a maximum or a minimum of a linear function. This linear function whose optimal value you are finding is called the objective function. I'm going to write this in a few minutes. Of several variables subject to the condition that these variables are non-negative. Non-negative means greater than or equal to 0, and they satisfy a set of linear inequalities. Okay, the term linear means what? All the mathematical relations used in the problem are linear relations. That means they are not quadratic, cubic, they are all linear relations. Okay, while the term programming refers to the method we are using to determine a particular program. For example, a firm might want to maximize its profit. A consumer may want to maximize its utility or satisfaction. A factory might want to minimize its cost. So these are all the programs. Okay, so hoping students have understood the definition of linear programming and the node. Let's now move forward. Let's look at what are the important terminologies involved in linear programming. So all students are requested to write the heading important terminologies in linear programming. So let's now look at these terminologies one by one. So first is the objective function. The first one is the objective function. The linear function z, which is equal to ax plus by, where a and b are constants, where a and b are constants, and this function z, which needs to be maximized or minimized, is called a linear objective function. It is called a linear objective function. So let's revise the definition again. All students can clearly see that z equal to ax plus by is a linear function where a and b are constants. You can clearly see it's a polynomial of degree 1. All polynomials of degree 1 are linear functions. All the polynomials whose degrees are greater than 1 are non-linear functions. So z equal to ax plus by is a linear function in x and y. A and b are constants. Our objective is to either maximize or minimize this function z. So this function z is called the objective function, because either we have the objective to maximize this z, or we have the objective to minimize this z. So it's an objective function. Okay, you can write the variables x and y. The variables x and y are called the decision variables. The variables x and y are called the decision variables, because these are the variables whose values are going to decide whether the value of z is maximum or minimum. Okay, so I hope objective function definition is clear. The second important terminology, constraints. Okay, the second important terminology, constraints. The linear inequalities or equations or restrictions on the variables of a linear programming problem are called constraints. Okay, so the linear inequalities, we have done linear inequalities in class 11th mathematics. Linear inequalities or equations or restrictions on the variable of a linear programming problem are called constraints. Okay, remember we said that in the linear programming problem, the decision variables are non-negative. Non-negative means the conditions that x is greater than equal to 0 and y is greater than equal to 0 are called non-negative restrictions. They are called non-negative restrictions. Okay, so once again revising, objective function is z equal to ax plus by, and we need to either maximize or minimize it, where x and y are the decision variables and a and b are the constants. We need to maximize or minimize the objective function with respect to some constraints. Constraints are the linear inequalities or equations or restrictions on the variables of the linear programming problem. What are the variables, guys? The variables are nothing but x and y. So if I put any restrictions on x and y, all these are called constraints. And the non-negative constraints are x greater than equal to 0 and y greater than equal to 0. That means in our entire lectures on linear programming, we will be assuming that the decision variables are non-negative. That means they are greater than or equal to 0. Okay, let's now move on to the third terminology, optimization problem. Optimization problem. A problem which seeks to maximize or minimize a linear function. A problem which seeks to maximize or minimize a linear function subject to certain constraints, as determined by a set of linear inequalities is called an optimization problem. Is called an optimization problem. Okay, so that problem which seeks to either maximize or minimize a linear function. This linear function is nothing but the objective function, subject to certain constraints as determined by the set of linear inequalities. This whole problem is called the optimization problem. Okay, so hoping all students have understood the terminology till now. Now, let's quickly look at the graphical method of solving linear programming problems. But before doing that, let me give you an example of a linear programming problem. An example of a linear programming problem. I'm giving a hypothetical example just to show how a linear programming problem looks like. Okay, maximize z, which is equal to 250x plus 75y, subject to the constraints 5x plus y less than equal to 100, x plus y less than equal to 60, x greater than equal to 0, y greater than equal to 0. Now it's a typical linear programming problem. Guys, this is nothing but my objective function. This is my objective function because I need to maximize it. What are my decision variables? X and y are the decision variables. So whatever decision variables are there, usually I write them below maximize. I need to maximize with respect to x and y. Okay. So these are my decision variables, and these three equations are my linear inequalities. You can see they are all linear. The degree of the polynomial is 1. Linear inequalities. And this within linear inequalities, this is nothing but my non-negative constraint. This is nothing but my non-negative constraint. Okay, so now let's look at the graphical method to solve this problem. Okay, let's look at graphical method of solving linear programming problems. Okay, graphical method of solving linear programming problems. Again, guys, let's get ourselves familiar with some terms in the graphical method before we actually start practicing questions. So our heading now is some important terminologies. Some important terminologies involved in graphical method. Let's look at some important terminologies involved in the graphical method. So the first one, feasible region. What is meant by a feasible region? So the common region determined by all the constraints, including the non-negative constraints, x and y greater than equal to 0 of a linear programming problem is called the feasible region. It is called the feasible region. So guys, that region which you are going to get when you solve all the non-negativity constraints together. So that common region you are going to get by solving and shading all the inequalities. When you shade all the inequalities, the common area you get is nothing but your feasible region. Okay, you are going to understand this in a much better way when we actually do a numerical. But before doing any numerical, you should be comfortable with all the terms. Okay, and then we can write the region other than the feasible region. The region other than the feasible region, okay, is called an infeasible region. That region which lies outside the feasible region is called an infeasible region. So I once again repeat, when you solve all the linear constraints and you shade the common area, that gives you the feasible region. All points outside the feasible region belong to the infeasible region. And then the second terminology, feasible solution. Feasible solution. So points within and on the boundary. Points within and on the boundary of the feasible region represent the feasible solutions of the constraint. They represent the feasible solutions of the constraints. Okay, so those points which lie either within or on the boundary of the feasible region, those points which lie within and on the boundary of the feasible region are going to represent the feasible solutions of the constraint. And then I can write any point outside the feasible region, any point outside the feasible region is called an infeasible solution. It is called an infeasible solution. So guys, feasible solutions will only lie within the feasible region. I repeat, feasible solutions are going to lie within the feasible region. They can either be in the interior of the feasible region or on the boundary of the feasible region. But all the points which are outside the feasible region are infeasible solutions. Okay, hoping all students have understood this. And now within feasible solutions, now feasible solutions can be many. You can have lot of points in the interior and boundary. But now among all these feasible solutions, which is the optimal one? So here comes the next term. I am erasing the initial part. I am erasing the initial part, and here comes the next term. On the top of the screen, I am writing this. The third term, optimal feasible solution. Optimal feasible solution. So any point in the feasible region, that gives the optimal value, which can be either maximum or minimum of the objective function, is called an optimal solution. Okay, so I'm revising. Any point which lies within the feasible region, and that point gives you either the maximum or the minimum of the objective function. That means that point is either maximizing or minimizing your objective function. Then that point is called the optimal solution. So among many feasible solutions, you have one optimal solution. Or you can even have two optimal solutions. One will be maxima, another will be minima. Okay, so now let's do some important theorems. So theorem 1 for this particular lecture. These are all important theorems based on linear programming. Let R be the feasible region. Let R be the feasible region for a linear programming problem. Let R be the feasible region for a linear programming problem. And let Z equal to AX plus BY be the objective function. Okay, when the theorem says when Z has an optimal value, which can either be maximum or minimum, where the variables X and Y are subject to the constraints described by the linear inequalities, this is the main term, this is the main statement now. This optimal value must occur at a corner point. Or I can say the corner point is also called the vertex of the feasible region. Okay, so this is the first theorem for this lecture. I'm revising the theorem again. Let R be the feasible region. This feasible region will contain all the feasible solutions for a linear programming problem, and Z equal to AX plus BY is my objective function, which I need to either maximize or minimize. X and Y are my decision variables. and they are subject to the constraints described by the linear inequalities. Then the optimal value of Z must occur at a corner point. Corner point is also called the vertex of the feasible region. So it means what, guys? It means given all this happens, this must happen. So from, I can say from here to here, this is my hypothesis. If this happens, then this is my conclusion. From here to here, the blue brackets, this is my conclusion. Remember, every theorem has a hypothesis and a conclusion. Hypothesis is a statement which we assume to be true. And given the hypothesis, we have a conclusion. So if R is the feasible region, Z is my objective function, which needs to be either maximized or minimized, and X and Y are the decision variables subject to the constraints described by the linear inequalities, then the optimal value must occur at the corner point. Now, guys, you must be thinking, what is the corner point? So we can write a note. A corner point of a feasible region is a point in the region which is the intersection of two boundary lines, which is the intersection of two boundary lines. Okay, so when I talk about a corner point or a vertex is nothing but the point of intersection of two boundary lines. I can show this to you in the form of a diagram, or students can look at this diagram just for reference. Okay, so we have X, we have Y. Okay, and suppose I plot two constraints. One is this constraint. Okay, and another one is this constraint. Another one is this constraint. So all students can see two constraints. And suppose my feasible region is this. Suppose this is my feasible region. The red shaded area. Hypothetically, I say that this is my feasible region. And if I ask you guys, what is the boundary point here? This is nothing but my boundary point, also called the vertex. It's the point of intersection of two boundary lines. One is the black boundary line, another one is the blue boundary line. So when both these boundary lines intersect, the point of intersection is the boundary point. So the theorem is telling us what? The maxima or the minima of the objective function must occur at the boundary point. That means at this particular point, the function will either have a maxima or a minima. This is what theorem 1 was telling us. Okay, and now let's look at theorem 2, another important theorem. Theorem 2. Let R be the feasible region. Let R be the feasible region for a linear programming problem. Let R be the feasible region for a linear programming problem. And let Z equal to AX plus BY be the objective function. Then, if R is bounded, I'll talk about what is meant by bounded in a few minutes. If R is bounded, then the objective function Z, has both a maximum and a minimum value on R. And each of these values occurs at a corner point. We have just talked about corner point a few minutes back, also called the vertex. Nothing but the point of intersection of the two boundary lines of R. So let me quickly revise the theorem. Let R denote the feasible region for a linear programming problem. Okay, and z equal to ax plus by is my objective function, which I need to either maximize or minimize if R is bounded. Now we can quickly write a note. What is meant by bounded? A feasible region is said to be bounded if it can be enclosed within a circle. So I can say that a feasible region is said to be bounded if you can enclose that region within a sufficiently large circle. Otherwise, it is called unbounded. So I can write unbounded means that the feasible region does extend indefinitely in many directions. If you cannot enclose a region within a large circle, that region is said to be unbounded. You cannot enclose it within a large circle. So the theorem is telling us if my feasible region R is bounded, that means you can enclose R within a large circle. Then your objective function Z will have both a maximum and a minimum value, and each of these is going to occur at the corner point. Let me give you an example of this. So guys, if you look at the diagram, what is this theorem telling us? Suppose again I have two inequalities. This is my one boundary line and this is my another boundary line. And suppose guys my feasible region is this. Suppose this is my feasible region. I'm writing in green, this is my feasible region. You can see that this feasible region is bounded. Why? Because I can draw a sufficiently large circle such that the region lies within the circle. So this feasible region is bounded because you can enclose this region within a sufficiently large circle. You can see a purple color circle on your screens. So given this, you can always have the corner point. This is my corner point, also called the vertex. And theorem 2 says that this point will either be a point of maxima or it will be a point of minima for the objective function. That means this, given that the feasible region is bounded, the corner point will either cause the objective function to be maximum or it will cause the objective function to be minimum. But on the other hand, if I have another diagram, now look at another diagram. Look at another diagram I'm drawing. Suppose my feasible region is somewhat like this. This is my one boundary line. Okay. This is another boundary line in green color. And suppose guys, my shaded area is this. Suppose this is my shaded area. Suppose this is my feasible region now. This is my feasible region. Now, is it bounded? No, because it's increasing up to infinity. It is not bounded. You cannot enclose this within a large circle because it has no limits. It will keep on going, guys. If you look at this, it will keep on going. It has no bounds. So now, according to theorem 2, your corner point or vertex will not be a point of maxima minima because your hypothesis is not true. Your feasible region is not bounded. Your feasible region is not bounded here. So you will not get a maxima or minima for this function. This is what theorem 2 tells us. So we can write a note that if my feasible region R is unbounded, as you can see in the diagram, your feasible region R is unbounded, then a maximum or a minimum value of the objective function may not exist. If your R is unbounded, a maximum or a minimum value of the objective function may not exist. Okay, so students, this is where I intend to stop in this particular lecture. The objective of this lecture was to introduce to you some important terminologies in linear programming. So it was a theoretical lecture. But in the next lecture of linear programming, we will actually look at the graphical approach to solving linear programming problems using the corner point method. Today, the objective was just to make all students comfortable with the terminologies and the two important theorems we have done. We actually start solving practice problems on linear programming in the next lecture of linear programming. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.